All right, so here we are, 2.7 graphs of rational functions. So, of course, we can use Desmos just to graph these functions, but it's also important for us to kind of know where all these different parts are coming from. So we're going to kind of mix Desmos and kind of the algebra that we've been doing and add a little bit more to it in the form of those other asymptotes that I mentioned before. All right, let's see what we're working with. So general procedure for graphing rational functions. We're not necessarily going to do it exactly this way every single time because we will lean on Desmos a little bit more, but in general, find any vertical asymptotes, determine any horizontal asymptotes, find the x-intercepts, plot the y-intercept. Right here, step 5, this is where we're going to deviate a little bit. We're going to lean on Desmos here to plot a few points on each side of the vertical asymptotes. We're going to really be using Desmos to kind of see what the graph looks like and draw some curves that match it and have the appropriate behavior at the asymptotes. We want to know whether it's increasing into the asymptote, decreasing, whether it's flattening along it that way or it's going up to it, what the behavior is at the asymptotes. This is last step here where we kind of put it all together and actually make a sketch. That's where we're going to be using Desmos. Okay. All right, let's go ahead and keep going. So let's graph this function. Well, a lot to do here. It's a pretty simple function. It's not that complicated. We're dealing with first degrees on the top and the bottom, so not a lot of advanced algebra going on here in solving it. Let's find our vertical asymptotes. So vertical asymptotes are going to be at what makes the denominator equal to 0. Pretty easy to figure that out. X equals -4. All right. Next thing, horizontal asymptote. We have a degree 1 and degree 1. They're equal, so it's a ratio of the leading coefficients, 3/1. So that's y equals 3 for a horizontal asymptote. Some other things that we want to know, like the y-intercept and the x-intercept. I don't remember if I'm doing these in the appropriate order, but y-intercept will be if I plug in a 0 for x, get 3 times 0, get 0/4. We're going to get a y-intercept at 0. So, or 0, 0, I guess, right? The x-coordinate is 0, the y-coordinate is 0. X-intercepts, that's when the numerator equals 0. So we got to solve this equation. Divide by 3, figure out there's also an x-intercept at 0. You already kind of knew that right there, right? After this is where we really need to rely on some technology to help us. But I'm going to sketch in some stuff that we know. I'm going to make my asymptotes yellow after I do something. Okay. When we're graphing these, we're not looking for an exact perfect thing. We want a sketch. So that's what I'm doing here. So I've got vertical asymptote at -4, x equals -4. So that's right here, vertical line right there. Horizontal asymptote at y equals 3. We do know there is an x-intercept and a y-intercept at 0, 0. So there's a point right there. Okay, here's where I need to rely on technology to help me make this sketch a little bit better. I already kind of know what this is going to look like. There's going to be kind of a curve here that goes like this, and then one over here. But I'm going to go ahead and lean on Desmos for the help. So equals 3x over x plus 4. Okay, here's our function. We can see what's going on here. We got a curve down here, and we have a vertical asymptote at x equals -4. So right there. And a horizontal asymptote at y. Let me clear away this screen real quick. Clear away. And y equals 3. 3. Let me make those both dashed. So to make it dashed, you click and hold right there, and it brings up this. I'm going to make them dashed. And I'm going to make them both blue. I like my asymptotes to be blue. Okay. I'll zoom out a little bit too, just to give myself a better idea of what I'm looking at. Well, I don't know that I need to zoom out so much. Sometimes, just like polynomial graphs, we'll want to change our y-axis a little bit. So I'm going to do that. I'm going to make it like -20 to 20, just to give me a little better idea. Okay, so yeah, you can see how it's up in this region. It's kind of going up to infinity along the vertical asymptote and then down along our horizontal. And then over here, it's going down to negative infinity along our vertical asymptote, and then out here up approaching our horizontal asymptote. So I want to show that on my graph. Again, I don't need it to be perfect. I'm just going to sketch what I'm seeing here. All right, so something like this. And here we're getting something like that. It's not perfect. It's a general sketch of what I'm seeing. To make it better, maybe I would want more of a horizontal or more of a vertical asymptote and more of a horizontal, and kind of shift my graph to see more of it, but you get the idea. This is a sketch. I want to see intercepts. I want to see where the asymptotes are, and I want to see the general shape of the graph. That's really all we're looking for. All right. Now, we have the opportunity to have some other types of asymptotes. And these are going to happen when the degree of the numerator is greater than the degree of the denominator. So when n is greater than d. Now, depending on how much greater, how many degrees greater, we're going to have different types of asymptotes. So if it's 1 degree greater, our asymptote is going to be a first degree polynomial, a line with a slope. If it's 2 degrees greater, it's going to be a second degree graph, a quadratic, a parabola. If it's 3 degrees greater, then it's going to be a cubic asymptote. We're actually going to take a look at all of these here in just a second, just some pictures of what they look like. Can get pretty wild. All right, so here is an example of a rational function where the degree of the top is 1 degree greater than the bottom. So we're having a linear asymptote, a slanted asymptote. You can see this is a linear equation for this particular asymptote right here. And that's making this graph down here, this one. It's got a slope of 1/2 and an intercept of -1 there. And you can see how our graph is following that sloped line instead of the horizontal asymptote that we had before. We also have a vertical asymptote, and all the other things can happen too. All right. And then here's this next example. We have a rational function here where the degree of the numerator is actually 2 degrees greater than the denominator. It's a 3 and a 1. And we actually have an asymptote here that is a parabola. You can see it right here. And it is crazy. I mean, look how this rational function is following that asymptote. We also have a vertical one. And over here, it's following that vertical asymptote, curves around the parabola, and then starts following it again. It is wild. These things are super cool. You can see how that parabola asymptote is shaping our graph. All right. And then here, last one that we're going to look at as an example. Here is a 4th degree over a 1st degree, so it's a difference of 3. And we get a cubic, a 3rd degree asymptote right here. Here's our 3rd degree asymptote. You can see how the rational function is following that and how the asymptote is really shaping the graph. It can get really, really cool. We're not going to do a lot with, I'm not going to expect you to necessarily come up with these 3rd degree and 2nd degree asymptotes, though I'm sure you could. It's really cool that they exist, though. All right. Well, how does it happen? How do we come up with these asymptotes? One way is using polynomial division. So we take our numerator polynomial, divide it by our denominator polynomial. And whatever we get, ignoring the remainder, is going to be the equation of our asymptote, whether that's a slanted asymptote, a parabola asymptote, whatever. So we use polynomial long division. So to do that, we set up a ratio of the leading coefficients, x squared over x. Okay, so it goes here. Then I distribute this. X times x is x squared, x times 1 is 1x. And then I have to subtract this from my polynomial. Now you'll notice, oops, I forgot to write x squared. You'll notice this isn't exactly lining up. This is not an x term. So sometimes when we set these up, you'll see people put in filler terms, so plus 0x, so that I have something to work with here. I'm going to distribute that negative. We get a negative and a negative. I can get rid of that. So x squared minus x squared is 0. Those cancel out. 0x minus 1. It's going to be minus 1x. Negative 9. I'm not doing anything to that. Nothing's modifying it, so it's right there. Okay. Then I need to get my next division step, right? To set up another ratio, negative 1x over x. It's going to be negative 1. Distribute that again. So I get negative 1x minus 1. And I have to subtract that from my polynomial here. So distribute here, I get plus 1, and I get plus 1, and we can come to more of that. Okay. Negative 1x plus 1x is 0. Usually we don't write that. I'll just not write that. They cancel out. Negative 9 plus 1 is negative 8. This is our remainder. For this process, I don't care what the remainder is. Unless the remainder happens to be 0, then that would tell me that these have common factors, and that kind of messes things up. But since it's remainder of 8, I don't care what the remainder is. This is going to be the equation of my slanted asymptote, x minus 1. So let's take a look at that. Let's go back to Desmos, x minus 1, x minus 1. Keep that in my head so I don't forget it, and go to work here. X minus y equals x minus 1. That is going to be an asymptote, so I will make it dashed in blue. And our function was x squared minus 9 over x plus 1. Cool. Awesome. We can see how it follows it. And if we zoom out, we can see even better how it's like really approaching that asymptote. We obviously also have a vertical asymptote at negative 1 that I could throw in here too, just to show all of it. And there we go. Let's zoom back in and get a little bit better look at it. There we go. So it's approaching both our slanted asymptote and our vertical asymptote. So clear? And we'll go back. All right. Now, what kind of asymptotes will this function have? This one is a bit of a trick because this numerator function and this denominator function have a common factor. So I'm going to skip this one, but I'll quickly show this is really the same thing as x squared minus 9 squared. So we can write this as x squared minus 9 times x squared plus 9. This factors even further, this one, because that's another difference of squares. This is x squared minus 3. So this factors as x minus 3 times x plus 3, and then x squared plus 9. You can see now they have a common factor, x plus 3. So technically, this is not even a rational function at all because they have a common factor. We got rid of this altogether. It's not even a rational function. Be careful with these, but generally, when you're given a problem like this, you can usually assume that this won't happen. But be careful. All right, find the equation of the slant asymptote. So this is already telling me that my asymptote is going to be a slant. We know that because the degree of the numerator is 1 greater than the degree of the denominator. So I need to do my polynomial long division. 3x squared plus x minus 2. All right. I ratio my coefficients. 3x squared over 2x is going to be 3 over 2x. So this is going to be the mx version of the equation of my asymptote. Got to distribute that. That's actually going to be a bit of a pain. It's going to be 3x squared. 18 divided by 9x. And now we need to subtract that from our original polynomial. Distribute this negative. This becomes negative. This becomes negative. Okay. 3x squared minus 3x squared cancel. 1x minus 9x is negative 8x. Bring down this 2. Okay, one more ratio. We got negative 8x over 2x. That's going to just be minus 4. Minus 4. Distribute that. We get negative 8x minus 24. And we need to subtract that. Negative, this is going to become plus. This is going to become plus. Negative 8x plus 8x, 0. Negative 24, negative 2 plus 24 is 22. This is our remainder. And again, unless it's 0, which would mean this is a factor of that, I don't really care. Since it's not 0, this is our asymptote. Y equals that is our asymptote. And yeah, why not? Let's just take a look at it. Y equals 3 over 2x minus 4. 3 over 2x minus 4. Perhaps I will get there. 3 over 2x x minus 4. 2x plus 6, and it was 3x squared plus x minus 2. Plus x minus 2. Okay. There would also be a vertical asymptote at negative 3. Okay, cool. Yeah, looks good. We can see that the graph is approaching both our slanted asymptote that we just found and x equals negative 3. I got that by kind of quickly solving what would make this equal to 0. All right, yeah. I'm going to undo the clear. Just see, that's what we got there. That's where our slanted asymptote occurred. Not too difficult, but, you know, kind of throwing a bunch of stuff together that we've learned throughout this chapter. All right, this will be the last one here. We're going to sketch this graph. We're going to try to put all of this together here. We got x squared plus 2x minus 12. Degree difference of 1. The numerator is greater than the denominator, so we are going to have a slant asymptote in this case. That's not necessarily the first thing I need to do, though, just in the interest of space, might as well just go ahead and get that one out of the way. I know that's going to kind of take a while, so let's do it. Okay, ratio x squared over x is x. Distribute that. Subtract. 2 minus 5 is going to be negative 3. Negative 3x over x is negative 3. Distribute that. That's negative 3x minus 15. That becomes plus and plus. Okay. That is remainder 3. So this is going to be the equation of our slant asymptote. We'll use that later once we get some of the other stuff. Vertical asymptote, this would be pretty easy. What would make that equal 0? So we have a vertical asymptote at x equals negative 5. That's right here. Even sketch that one in. The y-axis on this one is not labeled because I may want to use bigger values on it. I may not want to be counting by 1. No horizontal asymptote because we have a slant one. We want to find the x-intercepts and the y-intercepts. So let's go with x-intercepts. So set our numerator equal to 0. I don't think that's factorable. Doesn't jump out to me as factorable. Multiply to -12 and add to 2. No. So quadratic formula? -2 plus or minus the square root of b squared minus 4 times 1 times 12. So that's going to be -48. 4 times 1 times -12 is -48. Yep, okay. Over 2 times 1 is 2. Okay, that's the same as plus 48. So here we get, inside of here, we actually get 52. Square root of 52. That's going to be, let me just use my calculator. 2 root 13. All right, so we get -2 plus or minus 2 root 13 over 2. These both divide by 2, end up with -1 plus or minus root 13. Those are obviously the exact values. If I'm graphing it, I probably actually want these as decimals. -1 plus root 13. So I got 2.6 approximately. So 2.6 somewhere in here. And then change that to minus and get that decimal version, -4.6. 4.6, I don't know why I wrote that. So that would be, yeah, like right in here, pretty close to the asymptote. All right, then we have our slanted asymptote to sketch in. This is just not going to be great because of all the stuff we have here, but slanted asymptote is x minus 3. So that's, remember, 1 is the slope. Let's say this is counting by 2. So -2, -4. So -3 would be right in there. And a slope of 1 would be up 1 over 1. Up 1 over 1. I'm kind of going to the middles because that's what it would be. And I'm just going to use the line tool to draw that. Okay, that's my slanted asymptote. All right. Let's take a look at this one on Desmos because I'm worried I made a mistake. Denominator is x plus 5. Let me clear this real quick. Clear these, I can come back to them. Numerator was x squared plus 2x. 12. All right, and we said we had a slanted asymptote at x minus 3. That seems to check out, and a vertical asymptote x equals -5. All right, that does seem to check out. So I'm going to go back to, let's kind of take a look at what I did there. Undo the clear. I think maybe my, oh, I see. My line is not accurate. I was doing a slope of 1, but I forgot that I changed the scale here. Let's just do it this way. Let's just say it's 1 and only graph the part that we can fit on there. So our intercept is right there, -3, 1, 2, 3. Slope of 1 is up 1 over 1. Yep, there we go. That looks better. That makes it fit the part that we were seeing. And the only part we're actually going to be able to graph is this upper section. So I will sketch that in and just, we'll be happy with that part. pretty difficult to draw in here. So remember, you know, those asymptotes are going to cross, and we're going to have our other section down in this region, and we can see it on the graph. You can see this. Well, things are on the screen. We're missing it, right? Because we're kind of cutting off this whole corner of the graph. We're not seeing that. That's okay. We did our best with the graph that we had. All right. That's gonna be the end of the video. I'll probably do an example of another video where I do a couple more examples of graphing these in the future, and we'll practice this a little bit tomorrow. I'll see you guys in class. Bye.